So if I have a spring that has a natural length here of, we'll just say 1 meter, I then attach a mass to it. So same spring, but I attach a mass to it. That's a 1, and this is ideal spring. I attach a mass to it, and the mass just sort of hangs there in a new equilibrium position. So this is the new equilibrium. If this is here is 1.5 meters, and the mass that is tacked onto it will make this a 6 kilogram mass, we can calculate the spring constant. So if I do a force diagram here, I have mg acting down, I have kx acting up. X is how far it's been pulled from equilibrium, which is here. So I have k is equal to, put in the intermediate step, let's assume that down is positive. So mg minus kx equals mass times 0 because it's equilibrium. So mg equals kx. K is equal to mg over x, which is 6 times 9.8, divided by how far it's been pulled from equilibrium, which is 0.5 meters. And then if you work through that, you end up with 117.6 newtons per meter. Now, if I stretch this down even farther, so that's equilibrium. Now I'm going to pull it down a little bit farther. How do I deal with that? Is that my displacement from that equilibrium, or is that my displacement from that equilibrium? Well, it turns out it all depends upon how much you want to take into account. And so that's what we're going to be doing in this video. And so I'm going to flip over and we're going to go through some math. Woo! Set up my situations. So this is equilibrium. This is equilibrium. And this is not equilibrium. So this distance right here, we're going to just make y sub 1, and we're going to make this y sub 2. Now, I know that in this case, we had just worked through it. This is some mass m here, that mg is equal to ky1. And so we're going to sort of put that on hold for a second. Over here, if I treat this as my equilibrium, because that's really how far the thing has been stretched, this distance is y1 plus y2. I pulled it down to here and I let go. So if I look at the forces acting on it, I have k times y1 plus y2, and then mg acting down. So I have k y1 plus y2 minus mg. I guess I'm now making up positive, minus mg equals mass times acceleration. I have ky1 plus ky2 distributing, minus mg equals ma. Well, from right here, I know that ky1 and mg are equal to each other, so those will cancel out, so I'm left with ky2 is equal to ma. So in essence, what I have here is I can treat this as my equilibrium position, and I stretch it down to y2, but I just don't include the weight when I'm dealing with that. So I could treat it as I'm pulling it down from this distance right here, and I include the weight in my formula, or I pull it down from here and I ignore the weight. Either way, this is the way that textbooks tend to do it. And this is the justification for it.